Yes, so in the last class, we defined oracles and we had finished Lardner's theorem, right? Hierarchy theorems, Lardner theorem, and now we'll start a new way, learn a new way of defining complexity classes, which is via oracles. It will be actually be a new kind of Turing machine. We have seen deterministic Turing machine, non-deterministic Turing machine. Now this will be an oracle Turing machine, which refers to an oracle, oracle O. So what it does is it has three special states apart from the usual states, which so it goes into this query state with by putting a string y on the oracle tape, that this is a third tape. So input tape, work tape and oracle tape, and once it puts y and goes into query state, in one step, in the next step it will go either to q yes or q no. Okay, so q yes will mean that y is in the oracle language, it's a yes string. No will mean, q no will mean that it's a no string in O. Okay, so in one step, big problems get solved by referring to a hard oracle. So with this in mind, we can define complexity class PO. Okay, so this is the set of those languages L has polytime oracle TM using O. Okay, so these are not the set of languages which have polytime Turing machines, right? This can be actually much harder because it is referring to this oracle O. And similarly, there is NPO, which is L says that L has polytime oracle NDTM using O. So that's the only difference. Languages which have polytime oracle NDTM. So what will NDTM do? NDTM is the same definition, except again it has these three special states: Q query, Q yes, Q no, and it puts a string on the oracle tape y string on the oracle tape, and then accordingly, according to O, whether y is in O or y not in O, it will go to the next special state. Okay, so now we have mixed non-determinism with oracle. So you can solve difficult problems now. I mean, you cannot really practically solve, but theoretically this class has difficult problems depending on how hard O is. So let's make some quick observations. So O complement can be solved using O, right? That's what this is saying. Complement of a O just requires negation, and which you can do in polynomial time, right? So it's P to the O. So if O is in P, if you are using a polytime oracle, then this is not very powerful. So P raised to O is the same as P, right? Because this polynomial time Turing machine doesn't need to query O. It can just solve the problem by itself. So every language in P raised to O is in P. And third is, if you define exponential computation class as follows: Turing machine M that on input x takes time 2 raised to n. So this is Turing machine. The yes strings are essentially Turing machines M that accept x in exponential time. So with this definition of exponential computation, it is like exp, right? But this is a single problem. This is a single language which is in exp. And if you use this as an oracle, what happens? So p raised to exp this is equal to exp, because any problem which can be solved using excom can be solved in exponential time, because excom itself is in exponential time. So that's the maximum you need. And any problem in exponential time can be solved using excom, right? Because there is a Turing machine that runs for exponential time and solves it. So the same thing p raised to excom can do. And the last interesting thing is that it's also np to the excom. Okay, so p and np become equal under this oracle, equal to exp. Okay, because np is not I mean, the non-deterministic Turing machine, wherever it is using excom oracle, that can be simulated in exponential time, and wherever it is using non-deterministic bits, they can also be guessed in exponential time. So that basically is the proof. But let's write few words about this. So 1 only needs negation, so negate the answer of O. Right, that can be done in polynomial time. That's the proof of point 1. Point 2, where you want to show that p time polynomial time oracle doesn't change p class. So here the proof is simply ignore the oracle, tape, instead use the polytime Turing machine. Of O. Okay, there is a polytime Turing machine for O, so use that. No need for oracle. Third, which is p raised to excom equal to np raised to excom equal to exp. So that is just show that exp is in p raised to excom. Okay, any problem in exponential time, this can be solved using its Turing machine, which is exponential time Turing machine, and it can use this oracle, excom oracle. Only thing to note here is that this we set 2 raised to n time for excom, while exponential exp problems may require 2 raised to n raised to epsilon time, or 2 raised to n raised to c time, larger time, right? So, but that you can also simulate, because on the oracle tape you can put a larger string n to the c. You can use padding on the oracle tape to achieve this. You could pad the query string. That's just a small point that you should use in this containment. This is automatically, trivially inside np to the excom, because p is in np, and then this can be simulated in exp. Why? Because NDTM uses only polysized certificate and query string. Right. So everything in an NDTM is actually polysize. So you can guess the certificate and you can also find the answer to your query string in EXP. That's all. So once you have understood Oracle Turing machine and these Oracle based complexity classes, we can also we can now define a concept related to proofs. So a proof about complexity classes C1 equal to C2 or C1 not equal to C2. Okay, so equality proof or inequality proof, it is called relativizing. Relativizing. Okay, relativizing, relativization. If it doesn't change under Oracle. So if for all O, C1O equal to C2O, respectively C1O not equal to C2O, also follows. Okay, so a relativizing proof is one which not only shows an equality, for example, between complexity classes, but also under any Oracle. So here one remark I would like to make. So in general, C1 equal to C2 does not mean C1O is equal to C2O. Okay, this may not be always true. Two complexity classes may be the same, but under Oracle they may behave differently. Okay, so this is not a trivial thing. So just think about this as an exercise. Why is this the case? But if you show C1 equal to C2 or C1 not equal to C2, so I should also say here not equal to. Okay, so under Oracle everything may change. So this is not a given, but diagonalization proves actually this implication follows. So let's write that down. Diagonalization is relativizing. And the reason for this is the two properties that we showed before, proposition 1 and proposition 2. So because you can take the complement in the Oracle, so as long as that is the case, diagonalization is relativizing. So use propositions. Do I need 3? No, just 1 and 2. So diagonalization proofs generally that we have seen till now, they have all been relativizing because of this simple property that you can use negation, and if O is in this complexity class P, then P raised to O doesn't change. So this at the level of general Turing machines, not just polynomial time, but general Turing machines, what happens is we always design the Turing machine via a descriptor. to give a proof by contradiction. Okay, so in that case, it actually doesn't. All you need is the negation operator to be simulable. If you can simulate the negation operator, then that design goes through. So that's the reason. Okay. So based on this, we will show that P not equal to NP requires a non-relativizing proof. Okay, so this was shown by Baker, Gill and Soloway. In 1975. So this was shown by designing languages A and B such that P raised to A is NP raised to A, but P raised to B is different from NP raised to B. Okay, so with A as an oracle, P and P look the same. With B as oracle, P and P look different. Now, if you can show P not equal to NP using a relativizing proof, then this difference was not possible. The same, I mean, since you can do negation in polynomial time, the diagonalization argument will actually work in showing that P raised to A is not equal to NP raised to A. Okay, but that is not the case. So this means that the proof, if it exists for P not equal to NP, it has to be non-relativizing. So notice that A I have already shown you. A is just take A to be exp com. This exponential computation language makes P and P equal. So we have already seen that A equal to x com works. So what remains is to design the language B, oracle B. So we will design B via diagonalization. Okay, so this is interesting because we'll show that diagonalization proof will not work, in fact, by using diagonalization itself. So let's first define what is called a unary language of B. So for any B, define the unary language UB which is the collection of those 1 to the n for which there is some string of that length in B. Okay, so that's the unary language related to B. B is binary, UB is unary, it's only in 1. And you can immediately see, because of this, there exists quantification that UB is in NP to the B, right. So if you use oracle B, then what happens? I mean, the verifier guesses. Let's just quickly do the proof here. Verifier guesses X and verifies X in B. Okay. So the guess part it will do by an NDTM, and the verification part it will just use the Oracle B. So if X is in B, then this 1 to the n is in UB. Such that X is equal to n. Okay, so then it will know whether n is 1 to the n is a yes string or a no string of UB. So UB is an NP to the B. It can be solved by guessing and using the Oracle B. Okay, so now we just have to design a B such that UB is not in PB. That's the idea. So design B such that UB is not in PB by recursion. So we will use recursion in the definition. Okay, so that's the main idea. We want to find a B such that the unary language B is not in PB, it's of course in NP to the B, and we'll design it by recursion. So recursion and obviously diagonalization. So we'll use some Turing machine descriptor and simulate it and then negate the answer. Those kind of things we'll do in the proof. So let mi I is an Oracle Turing machine description. It's a descriptor for Turing machine, but an Oracle Turing machine, okay, without knowing what the Oracle is, right? Because the Turing machine description, it doesn't need to know what the Oracle is. It will just go in query state and immediately transfer to Q yes or Q no. Let this be an enumeration of Oracle TM in increasing order of I. Okay, so we are enumerating the Oracle TMs by descriptors, increasing descriptors. So now idea is incrementally construct B in the ith stage ensure that MIB does not decide UB in exponential time. Let's start with B empty. This is the initialization step, and let us now so the kind of invariant in every stage will be this thing written in orange. This is the invariant. Okay, every time we'll make sure that in the ith stage MIB, this Oracle Turing machine, which is using query strings which are smaller than the part of B that has been constructed. So, MIB will work, but it will not be able to solve UB on that part in exponential time. So, initially we take B to be empty. How do we grow it? That is the interesting part. So, in the ith stage, so we have declared before only a finite number of strings in or out of B. In the up to I minus 1 stage, certain strings have been declared to be in or out of B. So, their status is fixed, but they are only finitely many. So, let us go beyond that length. So, choose Ni to be larger than that length. Okay, that is the Ni which is still undeclared. We have not fixed whether it is in B or not, that we have not decided yet, and that we will do in the ith stage. So, here you run MIB on 1 to the Ni for 2 raised to Ni minus 1 steps. As follows. So, to decide whether Ni 1 to the Ni will be a yes string or no string in or out of B, we will do the following. This is how we will do it. Remember, this ultimately diagonalization trick has to come. So, you have to use somewhere negation of the simulation. So, problem with this MIB, running MIB, is that what if MI refers to a string, queries a string which is undeclared. So, current B will not be able to answer it, right. Remember that this is not the final B, this is only a current B. So, it may not have answers for everything. It is not an all powerful oracle, right. So, that is why we have to describe how to run this. So, if MI queries B on undetermined strings, whose answers B does not know, right. Then declare them not in B. So, which means that now B grows. In this step, B will grow. Okay. Second, if MI queries on determined strings whose status is determined, then in this case just be consistent. Okay, so whatever status of the string is, yes or no, that B will be able to give, and then you use that to continue the execution of MIB. So with all this, if in 2 raised to ni minus 1 steps MIB accepts one to the ni, okay, the way we have described above using 1 and 2, answer the oracle queries like this. MIB accepts 1 to the ni, then now there is the point to negate this answer by doing what? Don't put ni length strings in UB. Then declare all of 0 1 to the ni out of B. And if MIB rejects 1 to the ni or cannot give any answer, then what happens? So it then put a string of length ni, put an undetermined string of 0 1 to the ni in B. Okay, so yet undetermined string, there will be some string in 0 1 to the I of this type, put that in B, hence you have put 1 to the ni in UB.